Wait, so when you guys have, I know you guys have like the change control. Oh, you guys have coffee. I have like a whole drawer full of coffee. Because back then, I guess, cool.
Okay, so I brought the exams over for scanning this morning. I should have multiple choice results later today, and then later this week we'll be grading the free response. So I'll try to post just the multiple choice raw results so you can have an idea. But we'll need to combine it with the free response and crunch all the numbers so it won't. Don't be scared. You know, like your score could be a lot better than your multiple choice raw score, but that will just give you some idea how you did on multiple choice. I will not be in office hours today. If you're planning on stopping by for office hours, email me. I'll be there Wednesday, but I can't do it today. So no office hours today. All right, any questions before we start? Okay, so we got, we were talking about arc length, and we did this example last time. And so I have this function graphed here, this product of polynomial and exponential function. I'm going to talk about developing a function. I'm going to develop a function that will give me, say, arc length starting from 0. Say I want a function that will, as x increases, it'll track how much arc length there is along this red curve as a function of x. Could you do it? Could you write it out? Or has all the math fallen out of your brain over the weekend? So could you write a function? So I want to, and for arc length we called it little s. So I'm going to call it little s of x. Could you write a function that would give arc length as a function of x of the function f? He wants that the arc length would be the square root of 1 plus rf of x squared. Agree with that? That's not the arc length function. What is that? That's the rate of change, right? So to write the arc length function, we need that. He said the rate of change function. And that's what we found from the Pythagorean theorem, the square root of 1 plus the rate. So the arc length function itself would be integral from 0 to x of the. So yeah, so if I defined in GC, if I defined the rate function on a different line, then I could just use function notation here for the rate. But let's just go ahead and put the rate function in explicitly here. So it would be square root 1 plus. Right. So I'm gonna put rf of t squared, and so we can let and again, or I could. I could define the rate of change of arc length on a different line. I could define the rate of change of f on a different line, but I'm not doing any of that. So I can use, if you go to the math menu, go to total derivative. So I want the total derivative of what? F. X, t, and then dt. And that should do it. So that should give me the arc length function, and so now I want to find out how long is the curve or the arc length from 0 to 5. How can I do that? I want to find out how far would you have to walk in the units of the axes. How far would I have to walk on this curve to get from x equals 0 to x equals 5? What should I do? S of 5, right? That's exactly what our arc length function does. Not well, though. Something's wrong. What's that? Derivative. Why do I need the derivative?
Oh, you have dx.
Oh, dt. There, I see. Yep, see that? That's good. Good job. Okay. So here's showing us. All right, so here's showing us that if I started at 0 and I walked along the red curve to 5, it would be 11.6 units, 11.6 axis units. Okay, now I want to know the arc length, but now starting from 1 to 4. So I'm going to start at x equals 1 and go to 4. And I want to do this as simply as possible. So what can I put in to get the arc length starting at 1 to 4? He wants s of 4 minus s of 1. Will it work? Yeah, because we can get all from 0 to 4 and then from 0 to 1 and subtract that off, right? So that would be, so this would give me the arc length from 0 to 4. And then I want to subtract off the arc length from 0 to 1. And I get that. Okay, what's a different way to answer this question? How can I answer that question again in a different way? He's suggesting the integral from 1 to 4. Will that do it? Yeah, so let's start at 1 instead of starting at 0. And then if we started at 1 and then took it to 4, we would should get the same number. So I'm going to show you that kind of from here on out with these accumulation functions, we're going to structure them a different way. So I'm going to put 2 arguments in here. So instead of just x, I'm going to put a and x. And then instead of 0 here or 1, I can put a. Okay, so what this does is, so I still have just the one independent variable x, but I have another argument that lets me change where we start from. Make sense? So now if I want to do this again, so now I want to show from 0 to 5 again. What do I need to write now? And then function notation. It's got to match. I'm going to call upon this function. The arguments have to match the arguments I defined, right? So if I want that from 0 to 5, I should write now 0 comma 5, and I get that same value. And then same with these. According to how my function is defined now, I'm including 2 arguments. The first argument being my a value. Did I do something wrong? 4. The 4 was the example. There we go. Okay. And so from now on, when we're doing these accumulation functions, we're going to use this way. We're going to have 2 arguments. The first argument being the starting a value, so we can change that. But but then there's still the one independent variable x. Once we fix, so that this first one's like a fixed value that we can change, but then x varies in the situation, right? X varies starting from a. Okay, so now given that, we have an alternative way to find this, right? Rather than going S04 and S01, how can I do this more succinctly now? Finding the arc length starting at 1 to 4. S, now start at 1 and accumulate to 4. And I'll get the same thing. Okay, any questions on that? Is that, please.
Are we sure we're recording? I know we.
Yes, I think I am. I got that all going. Yeah, it is. Thanks. Other questions? Okay, so we're gonna you'll have some homework on this, but it's now that we have the arc length function, we know the rate of change of arc length. We know how to create a arc length accumulation function. It's just like what we've done before, but just a new quantity, right? So it's all going to be all the same kinds of questions and problems, but now we're dealing with rate of change of arc length and accumulation of arc length. Okay, any questions on that? So you'll have some homework problems. I don't think we have any homework yet. Next topic will be surface area. Surface area. So we're going to generate surfaces the same way that we generated volumes, okay, by revolution. Solids, remember we did solids of revolution, and we found we generated the empty shell by revolving a function around the axis, and then we used cylinders to fill up the empty shell, and then we tracked the accumulation of volume as we did that. So now we're going to do the same thing. So here's a curve. It's a wavy increasing curve here. And now we're going to revolve that around the x-axis just like we did with volumes. And so here's a picture of what we would get in that case. It'd be like this wavy horn shape. And so our goal is an accumulation of surface area now, right? So starting from any value A, how much surface area, how much pink area there is generated as x increases. So for surface area, we use capital S. So little s is for arc length, capital S is for surface area. So can you write a general rule for capital S, A, comma, X? And we haven't gotten into the details yet, but you should be able to just write something down that would represent the surface area starting at A and then accumulating out to X. What would the general rule be for that? Again, we haven't gotten into the guts and the math of it, but you still should be able to write something down that would be a surface area accumulation function. What do you think? Yeah. Uh-huh. Awesome. Did you hear what she said? She said the integral from a to x of the rate of change of surface area with respect to t dt. Is that what I have? Yeah. Perfect. Right? So what's our goal here in this class? Is to figure out what? Rate of change of surface area. Once we can figure out what rate of change of surface area is, we're golden, right? We can just write down these accumulation functions all day long. So the meat to this, or the work we have to do is, what is the rate of change of surface area? Okay, so let's take a look at it. So I'm going to do my sine as an example here to start. So just imagine that I have the sine. We'll go back to our basic sine curve from 0 to pi. I'm going to take that and I'm going to revolve it around the x-axis to make an empty shell. But now rather than fill it with cylinders, we're going to still have delta x intervals. X is still going to increase through delta x intervals. But rather than filling it with solid cylinders, we're going to take a look at what would we need to do in those intervals to accumulate surface area, right? So just imagine we got there's our empty shell, okay? And so we're going to let's take a look at those cylinders though that we did. And so when we were accumulating volume, what was the rate of change? How did we say what the rate of change was in this situation? He wants area of the base. Agree with that? Right, when we were accumulating volume, we were looking in the current interval, and we said the area that's, in this case, is black, right? So the area of that black disk on the edge of our current cylinder, right? That was the leading edge, right? The leading edge where the volume is growing, that's going to be the rate of change of volume, right? So it would be the area of that black disk or the area of the base of the current cylinder, right? So now what would it be for surface area? So if you think about this, we're accumulating surface area, what is the leading edge, right? So what is the leading edge that is, if the surface area is growing, what would the leading edge be to accumulate surface area? Daniel?
The
He wants the circumference of that. So for volume, it was the area, that black area. He's saying the circumference. Is that the leading edge that kind of sweeps out the surface area? Does that make sense? Right. Okay, so what is the circumference of a circle? So I'll draw it here. So we're gonna, the rate of change of surface area would be, what's the leading edge as the surface area accumulates, would be that, kind of like that edge right there. That's what's growing to leave the surface area behind, like kind of sweep out surface area. And so, what is that? That's circumference, right? Circumference is 2 pi r. What is our independent variable here? X or y? Is x increasing through delta x intervals, or is y increasing through delta y intervals? X, right? X is increasing through delta x intervals. So we need r as a function of x. R as a function of x. So what is r as a function of x? What is the radius? X coordinate, y coordinate, big change in x, big change in y. But big change in y from the x-axis, which is y coordinate, right? Y coordinate. So this is 2 pi y. We need that in terms of x, because x is our independent variable. Y is sine x. But in general, we could say 2 pi f of x, right? So this is our conjecture. Our conjecture is that the rate of change of surface area, looking at previous examples of arc length and volume and area, remember area, the leading edge, right? The leading edge of how the quantity is growing is our rate of change. And this leading edge, we're saying, is the circumference of that circle. That's what's kind of sweeping out surface area. So our conjecture is that the rate of change is this. So we're going to test it, okay? So is this the rate of change of surface area? So the way we're going to test it is with something that we know for sure. And so rather than doing the sine curve, let's do a half circle, and we can test it against the surface area of a sphere. Okay? So that's what we're going to do. All right, making sense so far? Any questions? Okay, so let's look at, rather than doing the sine curve, let's do the function for a circle, and this is a circle with radius 3. So the top half of a circle with radius 3 is a square root of 9 minus x squared. So that's my function. And so then we're gonna again let x grow through delta x intervals. And then again, we're looking at, we think that that 2 pi, that circumference of the cylinder in the current interval, we think is our rate of change function. So let's do it. So first of all, what surface area, what's the real surface area from 0 to 3? So from 0 to 3, what is the actual surface area? So it would be half of a sphere, right? Anybody remember the surface area of a sphere? Yeah. It is 4 pi r squared. So the surface area of a sphere, we'll do it right here. And so I'll call that yeah, so 4 pi, what's our radius? 3. But what are we doing? Just half, right? We're going to end up with half of a sphere because we're starting from 0 to 3. I'm going to take 4 pi r squared and divide it by. Yeah, but then if someone came along, they wouldn't know what you were doing, right? This is better, because if someone else came along, then they would know exactly what you're doing there. But you're right, it would be the same value. Okay, so there's our actual, and now I want to test it against our conjecture. So I've got the rate of, let's see. What did we say the rate of change of surface area is? Rate of change of surface area, we thought is? Circumference, 2 pi. No, so it'd be for any x value, right? For any x value, the r is the y coordinate. And so that's my f of x, right? So I'm going to put in f of x here. So there's my rate of change. And then my surface area then from 0 to 3 is? So I'm going to move this up here. Okay, so I got the real surface area of half a sphere. I got the rate of change of surface area. So now I want to do my function. Next. Go there. Okay, and what will the surface area function be? So the surface area of half sphere, HS is half sphere. From a to x, I should do what? Integral from a to of what's my integrand, or what am I? The rate, right? This rate function, right? So I've defined it this time, so I'm going to use function notation. So r sub s t dt. So there's my surface area accumulation function according if the rate was 2 pi f of x. And what do I need next to check it? So now I'm going to check it and see if we got it right. What do I do? Tell the person next to you. How am I going to check to see if we have the surface area set up, this whole surface area function set up correctly? Tell the person next to you. Okay, let's see. Someone in the back. Is it McKay? Did you tell me what I'll put in to check our surface area function? What should I write? He wants s sub hs from 0, 3. What do you think? Yeah, so we want to start at 0. We want to accumulate to 3. And we're expecting it to be same thing as half sphere. It's not, right? It's not. So something's wrong. We've put in the rate function correctly, the accumulation function correctly, but when we accumulate according to our conjectured rate function, it's not right, and it's not close. So let's go back and look at the picture here and try to figure out what is wrong with this. Something wrong with what we've assumed. Okay, but when we do this, this means delta x is super small. When we do integral, it does. So yeah, so if we make delta x smaller, that usually works, right? That usually takes care of it. But in this case, it's not taking care of it, making delta x small. So what is it about our assumptions here that isn't quite right? Anyone have an idea? Yeah?
I guess it's not just like a tiny ring. I guess you have to account. Oh wait, do you have to account for like the side of the where it is? Like where it's cut in half. Do we have to account for like that whole?
Oh, over here on the left?
Yeah.
No, it's something in the current interval. The problem is in the current interval. Any ideas? What's wrong with our assumption here? So what are we doing? We're adding up all these little horizontal pieces. Do you see that what we're accumulating is all these little horizontal pieces, right? And even when the the cylinders or the rings get really, really small, we're still adding up a bunch of little teeny horizontal pieces. And so what does it need to be instead? Let me make delta x bigger again. Vertical pieces. Will vertical pieces do it? That'll be actually the same problem. Both. That'll actually be too big. So here's the curve coming down like this. I'm adding up these pieces, right? And the curve is coming down like this. What should we add up instead? Yeah.
We should be adding the diagonal or the hypotenuse.
Yeah, we should be adding the hypotenuse. Like, so there's the vertical and then the dx and the corresponding dy. What we need to add together is that diagonal, not these little horizontal pieces from dx. But we need to be adding the diagonals together, and then when that gets small, that will match the curve and give us the right surface area. But we know what that is. We've done this. What is that? Yeah. So what instead of dx, we need it to be in terms of ds. Rather than doing the circumference dx, we just need to do the circumference ds. And let me show you how that goes. So what is surface area? 8 something surface area. Here we go. So that's the difference between, the difference between dx and ds is what type of like rings you take, or I call them ribbons, okay, ribbons. So when we did dx, why not? Okay, so when we did dx, our ribbons were like this. But now we need a different kind of ribbon, right? We need a different kind of ribbon that's like this. You see the difference? So that rather than them being like right-angled ribbons, so like dx is like right-angled ribbons, like just a cylinder, right? So but now we need the ribbons to be like have an angle, right? So that little length is ds, not dx. So they're not right angles anymore. So where does that come from? That actually comes from cutting a cone. So if you take those right angle ribbons that you need, if you take like a slice of a cone and then cut it and then flatten it out, that's the kind of ribbon we need. Rather than like the side of a tin can and flattened out, right? So watch it again. So these ribbons, the ribbons that we need, come from slicing a cone. It's called a frustum, okay? So part of a cone is called a frustum, and then if you flatten that out, you get the right kind of ribbon that we need in order to get ds instead of dx for our elements. So let's watch it here. So here is now for large delta x using those frustums, right? So these are the ribbons that aren't at a right angle, that are cut from a cone, right? And here's a smaller delta x. And so you see when delta x gets smaller, these ribbons of surface area are going to actually get the right surface area. So here's a real small delta x, 0.1. You see how those are matching the surface perfectly, rather than being like a stair step, what we had. Does it make sense? So we're going to take, rather than taking the horizontal dx with a right angled ribbon, we're going to take the ds ribbons, and what we're going to do is we're going to flatten those, flatten it out. So now this dimension is ds. This dimension is our perimeter, 2 pi fx. So our 2 pi fx was correct. It was correct. That idea is still the same. We got the ring, and it's generating the surface area. But not dx, not horizontally, but according to ds. So now, then what we know ds is, so rather than 2 pi fx dx, we just have 2 pi fx ds, and we found that's exactly what our arc length function was. Right? ds is going to be what? The rate of change of arc length dx. So we need to include this element right here, which takes us from dx to ds, but then we can still evaluate it in terms of x. Does that make sense? So this is the correct rate of change function, and then we know ds is all of this, and then we can still write surface area as a function of x. So there's our rate of change right there. There's our rate of change of surface area with respect to x. Okay, does the principle make sense? So let's go back to the sphere. And when we go back to the sphere, we should be able to get it now. So I want you to, no, that's not right. What was it? Yes. So I want you to, I'm going to take attendance. I want you to revise. What would you write in GC? How would you revise what I wrote here and write it out in your notes in GC so that I will actually be calculating the surface area correctly? And if we did capital S of 0.3, we would get the right thing, 56.54 or something. Okay, so I'm going to take attendance. Figure that out. So what am I going to do now? So what line should I change here? The black one? Okay, how should I change it? Okay, so the square root, that'll work, that'll get me the right thing, but we want the rate of change of surface area to include that because it does. Right? So you could inject that square root in there, but then this wouldn't be labeled correctly anymore. So it would be right, but we want the rate of, if we were going to call it the rate of change of surface area, we want it to include that square root. So instead, what can I do? Anna. Okay, so where should I put it? Here?
No, next to the
yeah, right. We're going to change the rate of change of surface area function to be?
the square root of 1 plus the rate of change of x.
Right, and I've defined that here, so I'm going to just use that. I could do that derivative here, but I've defined it already, so I can just use r sub f of x. Squared. Something was wrong there. All right, so to work, so all I had to do is change the rate. Once I get the rate function right, we know that's right, from our experience all semester, that the surface area accumulation is going to be integral of the rate. So once I get the rate right, which I just did, so is it correct? Yes. Why the slight difference? Why the slight difference? Okay, because the calculator, GC, is using numerical methods like chopping it up, delta x, into really small. It doesn't know delta x super small. It actually calculates things making delta x small enough, like 0.001. So it's using a numerical method to calculate that, because it doesn't know pi to all its digits, right? So it's using a numerical method to do that, and it's using a numerical method to calculate, get an approximation of this. So that's why it's coming out slightly different. But we can see we're the same to the nearest tenth, right? So we've got it right now. Okay? But GC doesn't calculate exact results. It just calculates it out to so many decimal places. So it's actually using this chopping up into intervals, just that its intervals is really, really small. And it's actually doing a sum. Okay? It's actually doing a sum, but not of super small intervals the way that we think of it when we do integrals. Okay, and so how'd the football go? Any more questions about this half sphere? Does it make sense now? All right, how about the football? So I want to get the surface area of the football properly inflated, right? So I'm going to start from scratch. I know that that's based on sine x rotated around the x-axis. So I'm going to start from scratch here. How do I need to start? What do I need to do? Samantha, what do you think?
So the rate of change function of surface area.
Okay. So we'll do r sub capital S x equals? What would it be?
So the 2 pi
2 pi
sine x,
sine x, good.
and then times the square root of 1 plus the rate of change of function squared.
Which is, and we can just write that. What is the rate of change of the functions? So our function, what's our function?
Times the sine x.
Yeah, so the rate of change is? People are saying cosine. Agree with that? So yeah, so again, we could write, I could define f of x in GC, and then we could put f of x there. I could define the rate of change of f using the derivative, or you can just put them in explicitly, right? Because they have the same meaning. Okay, someone else take over from here. How about Alan?
Sure. And then to determine the full surface area of the football,
Uh-huh.
you have to do S, and then have A and X for your two variables.
Good, so let's define the function, and then we'll use the function to get the area. So we're going to just define the whole function, meaning we'll get any surface area along the way.
And then you have an integral from A to X.
Let's see. Integral from a to x.
Of the rate of change of the surface area. You define above
Good,
with T instead of X.
good.
And then
How are we doing so far? Good. So all we got left, is it Andrew? No. Andrew is next to him. Sorry. So what do I want? I want to get the area of the football now. Surface area of the giant thing.
Okay, so then what you want to do is
0 to pi. There it is. Any questions?